Okay, recording is on, second half of Monday, November 16th, Math 4707. So here we were, and we had a theorem that says in a certain situation, we can apply Hall's theorem. Namely, if we've got a bipartite graph, which all vertices have the same degree, d greater than or equal to 1, then it's going to have a perfect matching, and better yet, the edge set will be a disjoint union of d different perfect matchings. And so we did an example of this, and we were about to prove that corollary. So, proof of corollary. Well, it's surprisingly easy to check the causal conditions. Let's assume that you know, G, this bipartite graph has the degree of every vertex equal to D. For all xi and x, y, j, and y. And let's check Hall's condition is satisfied. So what does that mean? If I'm given a subset of vertices on the left. So let me draw a picture of my graph. Here it is. On the left, we got the x. On the y, we got the y. And I'm assuming that everybody has the same degree. Let me draw it in such a way that everybody has the same degree. Maybe again 3. Let's see. Yeah. Okay. And so now, if I take some subset, actually that's too big a subset. Let me take a smaller subset. Suppose I take some subset of vertices x prime on the left. What I'm going to do in order to show you that the number of neighbors for that subset is at least the size of x prime is I'm just going to look at the graph that I get on the vertices x prime and the neighbors of x prime. So consider the subgraph on x prime disjoint union its neighbors, which are on the other side, and the edges between them. Okay, so let's take this proof and this picture over the other side, over to the other page. So what do we have here? We've got the x prime was just those two things, right? That was our x prime. And yeah, who are they connected to? Let's see. We're definitely connected to this one by that. This one's a neighbor. This one's a neighbor. This one's a neighbor, but I think that's it. So actually maybe what I should do is, no, I'm not going to name them. I'm just going to draw them. So I think we've got the first one, the third one, and the fourth one on the y side is our n of x prime. And the edges between them that we had were this one going straight across, this one all the way down. We had this one and this one, and who else? Ooh, there were more neighbors. I don't know why I thought that the neighbors was, yeah, because I see this edge went from, this edge went from there to there. So I'm still missing, oh, that's why. Somebody doesn't have enough, yeah. I was trying to make everybody have degree 3 here, and this one's only connected to 2 things. who else should I connect it to is, wait, did I? Sorry, I'm having trouble making a graph that fits my hypotheses. Yeah, let me redraw this graph. I'm sorry. Actually, you know what I should do? Let's just steal one that we had before that worked. Let's take our example graph. Okay. All right, here, if I pick some subset, x prime, I don't know, I'm gonna pick these two as my x prime. I'm gonna look who their neighbors are. Who are their neighbors? Let's see if we can carefully do this. This one is in their neighbors, this one, this one, this one, that one we already have, and that one we already have. I think that's it. Yeah. So that's n of x prime. Okay. So now let me redraw it with just those things there and nobody else. This subgraph that I'm talking about. So I'm going to get rid of all of the things that don't have edges coming out of x prime. And I don't need this. Okay, so this is the subgraph I want to consider on the right side. All right. And so what I want to do is say, let's count in two ways the edges that occur in this subgraph according to their left endpoint and according to their right endpoint. So count in two ways the edges in this subgraph. So I mean, that one, it's on x prime together with its neighbors. On one hand, it is exactly the sum over the things that are on the left side of their degree back in the original graph. Because, right, we've got them and we've got all of their neighbors are there. We didn't lose any edges that come out of them. And so I claim that is just the size of x prime times d. It's the same as the original degree in the subgraph. Okay. On the other hand, if we think about them by their right endpoint, it is less than or equal to the sum over the things that are in the neighbors of x prime of their degree back in the original graph. Because when you look at these, how many edges in this smaller graph are coming out of them, it's sometimes fewer. It's at most the original number. Like originally they each had 3 coming out. Well, in this subgraph, some are 1, some are 2. It's at most the 3. So that thing is the size of n of x prime times d is an upper bound for how many edges we have in the middle here. Do you see how I got that? And now these are both supposed to be the same thing. So what am I saying? d times the cardinality of x prime is less than or equal to d times the cardinality of n of x prime. But now cancel the d's. And we just checked Hall's condition is satisfied for this x prime. Seem okay? Questions? Okay. We'll consider that one proved. And now let me show you another one that's extremely similar. It's actually very closely related. That this one was related to the dance problem from the chapter 10 in the book. Our standard boys girls dancing, you know, that's the way this book is. But this one is the one that's perhaps equally culturally insensitive, the one about the tribes and the totems. So let me phrase it a different way, and then I'll explain why it's a version of the tribes and totems problem. Questions before I do another one? Okay. All right. Similarly, you're going to get a corollary to Hall's theorem. This one is going to be phrased as, suppose I've got a square matrix and it's got non-negative integer entries. No, excuse me, non-negative entries. So real numbers, non-negative entries. And all of the row sums and all of the column sums are the same number S. So I want to write down that hypothesis. A square matrix A. So let me name its entries. Aij, I goes from 1 to n. J goes from 1 to, is that right? Yeah, 1 to n. J goes from 1 to n. Has all of its entries are non-negative, and all the row and column sums are equal to S. I'd say S is positive, so that since they're non-negative, if S was 0, that would mean it's just a 0 matrix. Not very interesting. Then, two things. And it's kind of going to be like, the two things are going to be like our corollary and corollary to corollary. So, sorry. First thing, A and B. Let's see. First thing, A says, there exists a way to pick entries, one from each row and column, that are actually strictly positive. There exists a permutation sigma of the numbers 1 through n that's going to tell me which entry in each row and column to take. So write it like this. There exists a permutation so that AI sigma I is actually strictly positive, not 0 for every I. Okay. And B, so that's going to be like our corollary. B is going to be like the corollary to the corollary. One can write A as a sum of matrices that are permutation matrices. A is going to be S1P1 plus S2P2 plus ... SMPM for some positive real numbers. I guess I can assume they're actually positive. I wrote non-negative, but S1 plus, these numbers are going to add up to S, whatever the row and the column sums were. And the PIs are permutation matrices. Which means they've got one non-zero entry in each row and column, and it's equal to a 1. So they have exactly one non-zero entry, one entry in each row and column equal to 1. So just to give you an example, probably many of you have seen these, but here's a permutation matrix. All right, so lots of 0 entries, but there's these few entries, these ones that are the non-zero entries, and there's exactly 1 of them in each row and each column. Okay, so what is going on here? Let's compare this. Let me do this. Compare this with the totem problem from the book. So the book talks about this island with these tribes. Okay, so I'm going to draw this island. It's got some shape. And the island is broken up into a certain number of territories that, you know, tribes have. So like 4 territories that are supposed to be equal sized. I wish I had drawn a better equal sized. Okay, so those don't look very equal sized. Maybe I'll divvy it up a little more equally. I don't know. Oh, that still looks bad. Let's try that. Okay. And then there's these territories for these 4 different species of tortoise, I think they were saying. So maybe there's, let's see, the tortoise species territories are like this, and they are all of equal size. In fact, the same size as the territory of each tribe. And yeah, so let me call these the tribe regions X1, X2, X3, X4, and then these tortoise things Y1, Y2, Y3, and Y4. Okay, and what was the book saying is that if all of these regions that the tribes have and all of the tortoise territories are the same size and there's the same number of tribes and of tortoises, then there's going to be a way to match up tribes to tortoise species so that each one can pick as its totem a species that intersects with its tribal territory, right? Something like that. I don't know. It just makes me cringe just saying it. Let's put in some areas. Let me say that these areas are like this little area of intersection between X1 and Y1 is 2. And this X1 and Y2 intersect in an area of 1. And that one's a 1. And I'm going to make all of the tribal territories have total area 4. And all of the turtle areas also have 4. So I'm going to make a 2 in there. That means that turtle number 1, the Y1, has total area 2 plus 2 is 4. And notice tribe X1 has total area 2 plus 1 plus 1 is also 4. So I want those to be equal. S is equal to 4 in this story. Okay. They didn't have to be integers, but I'm making them integers. Why not? All right, so I'm going to put in some more overlap areas. 2, a 1, a 1, a 1, and a 3. Okay. My point is, this gives rise to one of these matrices, A, like I'm talking about, where the AIJs, they're going to be the overlap areas. And all the rows and column sums are going to be equal to a fixed number S. So let's get our matrix A out of this. A is going to have its rows and columns. Yes, rows are the X's. Columns are the Y's. The entry AIJ is the overlap between the X region and the Y region, the area. Okay, so for example, this 3 right here is the X4, Y4 entry. And this, this thing right here, no, let's not do a diagonal entry again. This one right here is between X4, between X2, which is in here, and the Y3. X2, Y3, we just said that was a 1, okay. All right, everybody see what I'm doing here to write down these numbers. So let me do the X row. The X row is gonna have a 2, a 1, and a 1, and a 0. Okay, everybody see where I got this 0 is because X1 does not have any overlap in area with the turtle area 4. Everybody see that, why that was a 0? Because this and this don't overlap. All right, good. Let's see, X2 has got a 2, a 1, and a 1. Also the same, in fact, same. 2, a 1, and a 1. Oh, I forgot to label an area. 1. Let's see, X3 is also a 2, a 1, and a 1, but it's shifted over a bit. It's with Y2, Y3, and Y4. Yeah, so it's 0, 2, 1, 1. And X4 is just a 1 and a 3. And it overlaps with Y3 and Y4. Okay, I think I did that right. Please, I'm going to look at my notes to make sure it looks like my notes. Yeah, it looks like what I had in my notes. Did everybody see where these things really are? They orange numbers show? I don't know why I didn't make them orange. Let's make them orange. And these are really the green, the tortoise. Oh, clever of me to make them green. They're tortoise territories. Everybody good? All right, and everybody sees the hypotheses. S equals 4 here is just saying that the row sums are all 4 and the column sums are all 4. Pretty good? And the fact that, you know, we have assertion A, right, would be the conclusion that they were talking about in the problem about tribes picking totems, right? The idea is that permutation should be like a choice of, I don't know, this, 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 and this, is saying there's some way to match up like X2 with Y1, X1 with Y2, X3 with Y3, and X4 with Y4, right? I guess I did it differently. In such a way that you've got each tribe able to pick a tortoise that it shares, has a positive area of overlap with to choose as its totem. That's the matching. Everybody see why A would be, the sigma would give you the matching. The one that makes this happen is this choice of the entries that are non-negative, one from each row and one column. Can I answer questions about that? Why part A is what their solution to the totem problem, that there's always, it's saying that there always exists such a solution. Okay. And then B, we'll see, really just comes from A. If we can show A, then we'll easily get B. So let's take this over here. Should I steal anything else? Let's steal this much. Oh, this is ambitious. Okay. Oh, we did it. So let's prove that A always holds when we have such a non-negative matrix like that. The part A always holds. And this is, again, a situation where we should set up a bipartite graph with the x's, the row indices, being the left side, the y's, the column indices, being the right side. And the question is, when do we put an edge between an x and a y? Well, we're trying to match along those edges. We should do it when their corresponding entry is positive, not zero. So the zeros are where we don't put edges. The positive entries are where we do put edges. Create from A, from such a matrix A, a bipartite graph. G, so it's got the X disjoint union Y, E, and right, this is just your row indices X1 through Xn, your column indices Y1 through Yn, with edges. E is just Xi's and Yj for Aij strictly positive. Okay. So like in our example, right, let's do this. X, Y, so here's X1, X2, X3, X4, Y1, Y2, Y3, Y4. And yeah, X1 is connected to the first three. X2 is also connected to the first three. X3 is connected to the last three. And X4 is connected to the last two. So it's not that it's a regular graph. It's no longer true that it's all the vertices have the same degree, right? It's this is not one where our previous corollary applies. But somehow I'm going to use this matrix that has the row sums all being 4 and the column sums all being 4. I'll show you that it still has Hall applicable to it. The Hall condition is satisfied. Okay. And so given a subset of the left side, so again, you just pick some arbitrary X prime over there, I'm going to convince you that the number of neighbors on the right side, n of X prime, is at least the size of X prime. Okay. So, whoop, coloring problem. Ah. What I'm going to do is consider the little submatrix whose rows are indexed by X prime, whose columns are indexed by n of X prime. Now this thing might be rectangular, right? Maybe I should actually, in our example, just see what this submatrix looks like. Okay, who's in n of X prime? That thing is, this thing is, this thing is. Is that it? Yeah, I think that's my n of X prime. So it actually is a rectangular matrix in this case. It's the thing that's indexed by these rows and these columns. Oop. Two, one, one, two, one, one. It's not that they all had to be non-zero, right? There could have been some zero entries in there, but that's okay. All right. And so what I want to do is consider the sum of all of the entries in this submatrix. I want to look at just all of them added up together. And count it in two ways. Compute in two ways. The sum of all entries in this submatrix. I'm going to do it by summing across rows, and then I'm going to do it by summing down columns. But I should get the same answer, right? All right. Summing across rows. It is, well, you got each row that's in X prime. And what you've taken is only the non-zero entries from that row, I guess. No, that's not true. You've at least gotten all of its non-zero entries. This was a poor choice of my X prime because there could have been some zero entries in here. But the point is you included all of the columns that contained the non-zero entries for up there. So my claim is this is equal to S times the size of X prime. Because you didn't miss any of the non-zero entries in a row from the way we defined which columns you took. Okay? Summing down columns. Summing down columns. Well, there it's a different story. As I go down this like Y2 column, I only took those two entries, but Y2 had some more non-zero entries in its column back up originally. So it's at most the original sum of S for each column. And you've got the number of things in N of X prime, that many columns. So this is less than or equal to S times the number of columns there. Everybody see why it's an inequality? Okay. But again, this thing on the nose was the same as the sum we were getting here, which we just said is less than or equal to this. So S times the cardinality of X prime is less than or equal to S times the cardinality of N of X prime. And now we cancel the S. To get Hall's inequality. Okay. And so because Hall's inequality is satisfied, we know there's going to be a matching. Say like this to this, this to that, this to this, this to this. And then when you go back into the matrix, that matching is along edges that correspond to non-zero matrix entries. So like the one that we just computed is this to this, this to this, this, and this. So we circled one non-zero entry from each row and column, and that corresponds to a permutation, sigma. So the permutation sends x2 to y1, so 2, 1, 2 goes to 1, 1 goes to 2, 3 goes to 3, 4 goes to 4. Does everybody see how that matching of the numbers 1 through n with the numbers 1 through n, that's a permutation. Okay. Questions about that? What about part B? Okay, so for the proof of B, well, first find this permutation sigma that gives you a bunch of non-zero entries. Okay, such that AI sigma I is actually strictly positive for each I. And I claim that that gives us a multiple of a permutation matrix that we can subtract and keep this thing non-negative. So let SI just be the minimum, excuse me, not SI. Let's let S1 be the minimum of these entries that were these non-zero entries that we circled. And I'm going to subtract off the permutation matrix times S1 in those positions. So S1 is equal to the minimum of these AI sigma I. So I goes from 1 to n. And let P hat be P minus S1 times the permutation matrix for sigma. Permutation matrix for sigma. Okay, so let's do an example. What am I saying? We had such an example of our A and the permutation that we were going to pull off, copy. Let's make that a little bigger. All right. And so what I'm going to say is, why did I call it P hat? A hat, not A hat. A and P. I'm getting confused as to who my matrices are. A hat is going to be A minus S1 times the permutation matrix for sigma. Okay, so first of all, if these are my entries in the AI sigma I, the smallest one is a 1. So S1 is 1. It's the minimum of that 1, 3, 1, 2, 1, and 3. And A hat is going to be A minus 1 times this permutation matrix. All right, that's a 1 there. And the point is, because we picked the minimum value that showed up there, A hat is also going to be non-negative. Let's see what it looks like. It's still got a 2 here. Now it's got a 0. Here it's got a 1. Here it's got a 1, a 1, a 0, a 1, a 0, 0, 2, 0, 1, 2, 1, 0, 0. Okay. And now this matrix A hat again satisfies the hypotheses of our theorem, but with S being S minus little s1. Has row sums, column sums, all equal to S minus S1. S, remember, was the original row and column sum was 4. S1 here was 1. Now they're all 3. And the reason was we subtracted little s1 times a permutation matrix. Its row sums and column sums are all little s1. And so that's how much we subtracted off from each of the rows and columns of the original matrix. And now you repeat step A or step B, whichever way you want to think about it. Repeat it on with A hat, replacing A. And we get to use induction on the number of zeros, or maybe I should say the number of non-zero entries. One thing is we created more zero entries when we did this because we made sure to actually pick the minimum here. And so some of those entries definitely turned into zeros. So if we look at the number of non-zero entries, A hat has fewer. And therefore, we can induct. We can say A hat already has the expression that we wanted. And if you go back, that means A has the expression that we wanted. It's a combination of permutation matrices with little si's that sum up to S. So I'm leaving out some of the steps in the induction and checking that all works, but I hope you could supply that yourself if you think about it. This induction is going to the inductive hypothesis is what we need to conclude it for A. Okay, so went a little bit over there, but that was, I think, all I was going to say about matching theory. We are done with chapter 10. Any questions about this before we turn our recording off? Maybe before I turn the recording off, let me tell you where we're headed next. I think we're going to skip chapter 11. We're going to go into chapter 12 on planar graphs. Then we'll be doing chapter 13, which has to do with graph coloring. It's also related to planar graphs. We'll spend a while in the planar graphs chapter next. And we have an exam coming up. It should be posted hopefully by late Tuesday night, but certainly by Wednesday morning. And again, it'll be a week-long tape home. All right. Any questions before the recording's turned off? What's after coloring? Great question, Jack. We'll see how much time we have, and I may return to some topics that we kind of skipped over. I don't know. We shall see. All right. So, any other questions? So we're